Today we will be talking about 15.2 line integrals. So we'll start out with the definition. If the function f is defined in a region containing a smooth curve C of finite length, then the line integral of f along C is given by the following. But the way we go about solving these line integrals is actually by using a definite integral. So we use the fact that ds is equal to the magnitude of r prime, which is written out over here. And then, so to go on further, the evaluation of line integrals. Let f be continuous in a region containing a smooth curve C if C is given by r of t equals x of t comma y of t, where t is bounded between a and b. Then the line integral is equal to the definite integral between b and a of the function times the magnitude of r prime. Alright, so this is our first example of a line integral. So we have the line integral of x squared minus y plus 3z ds. And this is the curve that we are taking the integral on. So first we need to parameterize this curve. It's from 0, 0, 0 to 1, 2, 1. So we will say that x is equal to t, y is equal to 2t, and that z is equal to t. And now in order to substitute for this ds term up here, we need to be able to find the magnitude of r, which these three functions right here make up r, and we need to find r prime. So we'll take the derivative. It's 1, 2, and 1. And we find the magnitude of this. So you get 1 squared plus 2 squared plus 1 squared, all under radical, so you get radical 6. Now we can replace this for our ds over here and multiply it by d of t, and make sure you replace all of your x, y, z terms with your new parameterized t terms. So you get t squared minus 2t plus 3t times radical 6, which is our magnitude of r prime, times dt. And then we also want to have our limits on here because it's a definite integral. So because of the way we parameterized, our t values are going to be between 0 and 1. So we put that on the integral. Now you can just take a normal antiderivatives and stuff and finish out the problem. So we'd get radical 6, 0 to 1, t squared plus t, that's 6 of t cubed over 3 plus t squared over 2, evaluated between 1 and 0. So we'll end up getting 5 rad 6 over 6. Here is one more example. So it says find the mass of a spring in the shape of a circular helix where t ranges from 0 to 6 pi, and the density of the spring is this. So first step would be to find the magnitude of r prime. So that equals 1 over rad 2 times the radical So now we need to take derivatives of each of these parts. So derivative of cosine of t is negative sine t, square it, plus derivative of sine of t is cosine t, square that, and plus 1 squared, which is just 1. And we would find that this all equals 1. So now to move on to the integral, we have that the mass is equal to integral from 0 to 6 pi. And then we're going to use this function right here, 1 plus, and we don't want to put z, we need to replace z with its parameterized form, which is over here, which is t, but you don't want to forget the multiplier in front of the vector, so it's actually t over rad 2. And this is times d of t. And the reason why there's not like this big thing up here is because it just ended up equaling 1, so don't have to worry about it. And now we just solve like normal, and you'd get t plus t squared over 2 radical 2 solved from 0 to 6 pi. This will give you 6 pi parentheses 1 plus 3 pi over rad 2, which is equal to 144.47.
In this video, I'm going to be talking about how to solve line integrals of vector fields. In this first problem, we're asked to solve the line integral of x cubed dx plus x dy with the following graphs. Y is equal to x squared, and x squared plus y squared is equal to 4. So starting with y is equal to x squared, my first step is to parameterize the graph. I could do so by letting t equal x, then y is equal to t squared. My next step is to take the derivative of x and y, and to get the derivative of x with respect to t is dt, and the derivative of y with respect to t is equal to 2t dt. And since t is equal to x, the limits of integration are from 0 to 2. Now that I have everything that could accept the line integral, so the line integral is equal to the integral from 0 to 2 of x cubed, which is t cubed times dx, which is dt, plus x, which is just t, times dy, and dy is 2t dt. I can simplify it and factor out of dt, and I get that the line integral is equal to the integral from 0 to 2 of t cubed plus 2t squared dt. I can now integrate, and I get that the line integral is equal to t to the 4th over 4 plus 2t cubed over 3 evaluated from 0 to 2, and that gives me 16 over 4 plus 16 over 3, and that is equal to 112 over 12, which is equal to 28 over 3. And that's your final answer for part A. Part B asks to use a path of x squared plus y squared is equal to 4. In order to parameterize this equation, I'm going to use the fact that x is equal to r cosine of t and y is equal to r sine of t. And since we have an equation of a circle, we know that r is equal to 2. So x is equal to 2 cosine t and y is equal to 2 sine t. Taking the derivative of x and y, I get that dx is equal to negative 2 sine t dt, and dy is equal to 2 cosine t dt, and t goes from 0 to pi over 2. So the line integral then is equal to the integral from 0 to pi over 2 of x cubed, which is 2 cosine t times dx, and this should be cubed, and dx is equal to negative 2 sine t dt plus x, which is equal to 2 cosine t times dy, which is equal to 2 cosine t dt. I could simplify and I get the integral from 0 to pi over 2 of, that becomes an 8. So 8 times negative 2 give me negative 16 cosine cubed t times sine t dt plus 4 cosine square t dt. Go factor out the dt, and I get the integral from 0 pi over 2 of negative 16 cosine cube t sine t plus 4 cosine square t dt. I could break up the integral into two parts, and I could get the integral from 0 to pi over 2 of negative 16 cosine t and cube times sine of t dt plus the integral from 0 to pi over 2 of 4 cosine square t dt. Integrating the first one, I see that if I let u equal to cosine t, then my du becomes sine of t dt. Should be negative. And switching the limits of integration, u of pi over 2 give me 0, and u of 0 should give me 1. I have one negative, another negative, and if I flip the limits of integration, that'll give me 3 negatives, so it stays negative. So I get the integral from 0 to 1 of negative 60 u cube du, and this one becomes 4 cosine square. We can use the power reduction formula to simplify, and we get that cosine square is equal to 1 plus cosine. We double the angle, so you should get 2t divided by 2. The 2 cancel out with the 4. And I get that the integral becomes the integral of from 0 to pi over 2 of 2 times 1 plus cosine of 2 pi of 2t dt. I'm going to integrate this one, and I get that the line angle for this portion becomes 2t plus 1/2 sine times 2. So the 2 cancel out with the 2 in the front, and times 2t evaluated from 0 to pi over 2. And this one becomes, integrating with respect to u, I get the u to the 4th divided by 4 times negative 16 evaluated from 0 to 1. This simplifies to negative 4. This is equal to negative 4. And I'm adding this one with this one. So plugging in pi over 2 for the expression, I should get 2 times pi over 2 plus sine of 2 times pi over 2. The 2's cancels, and I'm just left with sine of pi plus pi. And that's 0. So my final answer is pi minus 4.